Hi, everyone. So today we're going to talk about sequences and sort of start pushing into series a little bit. Next week we'll finish up series, and in particular we'll look next week at all of the different convergence tests, most of which you probably saw or at least applied in a Calculus 2 class, but we'll talk about them at a more fundamental level in terms of proving them. But we want to start today with with sequences. And you've probably you've certainly thought about sequences before. We talked about sequences back in chapter 1. So I've just sort of put up here formally a couple of definitions. So the first is the definition of a real valued sequence. So a real valued sequence, I mean, we often just sort of informally think of it as like just a list, an ordered list of real numbers. But we can actually just define it as a function which takes as inputs natural numbers and spits out real numbers, right? So if we think of it in this way, then sequence terms are just denoted by a of n, right? So the nth term of the sequence, and we often just write this as a sub n. We can also talk about, once we have a given sequence, we can talk about subsequences. And formally, we can actually think of that as a composition. So if phi is a function which takes as its input natural numbers and spits out natural numbers, so it's a function from n to n. If that phi is a strictly increasing function, then a composed with phi forms a subsequence, and so that subsequence would be a of phi of k, and we just denote a of phi of k as a sub n sub k. So again, here I'm saying phi sub k is equal to n sub k. The idea here is phi tells you sort of, so when n is 1, let's say that phi of 1 is 4. So that tells you that the first thing you're going to take in your subsequence is the fourth element of your original sequence. Okay, so a sub n sub 1, well, n sub 1 would be 4 in that case. And so the first element of your subsequence would be the fourth element of your original sequence. Now, again, often we just sort of write it like this and understand that we're talking about some subsequence, and that's fine. But this is sort of one way to formally define them. It is occasionally helpful to think of these as functions, but more often than not, we don't. This is just a really nice, convenient, compact way to write these things. A couple of notes. So the first is that we're right now going to be talking about, so we call these real valued sequences. You may also just call them sequences of real numbers, but you can take sequences of lots of things. So you can take sequences of matrices. You can take sequences of functions. You can take sequences of all sorts of things. So for the purposes today, we're going to be talking about real valued sequences or sequences of real numbers, but later on we'll say something about sequences of functions as well. So I just want to kind of point out that these aren't the only kind of sequences one can talk about. And then similarly, you can have subsequences of any type of sequence. So just a note there. So just to remind ourselves, again, these are ideas that we really talked about back in chapter 1, but another quick definition. So we say a sequence, call the sequence again a sub n, converges to a real number L, and which we denote by the limit as n goes to infinity of a sub n is equal to L if for every epsilon greater than 0, there exists a natural number n such that an minus L can be made less than epsilon whenever little n is greater than capital N. So I'm looking Um, I've sort of written it ever so slightly differently, although the same in actual definition as what's in the book. But again, the idea here is sort of, right, and again, this is where it can be useful sometimes if I want to sort of visually think about a sequence. So think about here, like this is n, and this is a sub n, and so I can plot, right, the values of my sequence, and so whatever they happen to be doing, sort of, oh wait, there wouldn't be one at 0. Oops. So there. Okay, so you're starting to get the sense, right? If I look at this sequence, and this is a visual representation of my sequence, it seems to be settling down, right, to some limiting value, I don't know, maybe around here. So there's my L. And so what this definition is saying is that for any epsilon I give you, this epsilon will sort of define a band around L. It should be the case that if I go out far enough in my sequence, all of the terms are within these epsilon bands. And I'm not a very good artist here, but right, so here it looks like sort of once I get past the third term here, all of these terms of my sequence are within epsilon of L. Okay? Now, of course, if you make epsilon smaller, then you may have to go out further. If you make epsilon even smaller, you may have to go in. But if we can sort of always win this game, right, for any epsilon you give me, I can choose this capital N such that if I go beyond that capital N, all the terms of my sequence are within epsilon of L, then I'm good. And this is, again, exactly the same definition we saw in chapter 1. The book works through an example of sort of, okay, if you're given a particular sequence A sub n, you know, how do you find that epsilon? And I'm going to give you a few of those just to play around with and refresh your memory on the homework and sort of, again, get back into that mindset of thinking about these things. But the real focus for this video is sort of more on a more theoretical level, what sorts of things can we prove about sequence convergence? All right, so we've got sort of the basic definitions down. And once we have those, there's sort of a whole bunch of theorems we can sort of immediately prove straight from the definitions. Okay? The book gives the proofs of all of these theorems. I suggest you take a look at those because they're pretty straightforward, just sort of applications of the definitions. So I just sort of briefly recap what some of those theorems are because we're going to use them. But I want to spend our time today focusing on some of the harder results and really working through those proofs. So take a look at these proofs. Make sure you feel comfortable with them and understand them, but we won't spend a lot of time going through all the details here. So the first theorem is that the limit of a sequence is unique. So if your sequence converges to some limit, it can only converge to one limit. It can't converge to two different limits. That's just not possible. Okay. The next theorem says every convergent sequence is bounded. All right, so let's think about this one. Sort of the spirit of the proof of this is, well, if my sequence is convergent, then that means if I go out far enough, it's getting really close to some value. Okay? So once I go out far enough, it's going to be close to that value. And since it's close to that value, it can't become unbounded far out, right? Because it's got to be close to L, whatever it converges to. So if I know that going out far enough, I'm within, say, distance 1 of L, okay, then if I look at all the earlier terms, well, they're all individually finite values. So the first n terms are whatever they happen to be. And then beyond capital N, I could, for example, control my sequence to make it always be within 1 of L. Okay? So I have this sort of infinite tail of the sequence is bounded by between L minus 1 and L plus 1. And then the first n terms in the sequence, well, they're all individually finite, and so they have some maximum. So I can sort of bound my whole sequence in this way. So that's sort of the second result. And again, the book has the proof, so read that carefully, but that's sort of the spirit of it. The next one, if A is an accumulation point of a set A, then there exists a sequence AN of points that are a subset of A. So there exists a sequence in A such that AN converges to A. So the idea here is if you have an accumulation point, you can always construct a sequence of things in your set that converge to that accumulation point. That may seem sort of unnecessary right now, or it may not be obvious why one would care about this. But for example, remember that accumulation points of a set do not necessarily lie in that set. Okay? They may, if your set is closed, for example, that it contains all of its accumulation points, but it might be an open set. So there might be sort of these points that aren't accumulation points that are not in A. But you might know that everything in set A has some nice property. And you might like to show that the accumulation point also has that nice property, even though it's not formally in the set A. And so a common way of doing this is to construct a sequence of things that converge to A, show that since that sequence, every element of that sequence is in A, everything, all of these things have the nice property, and then somehow show that in the limit, those properties carry through. Okay, so this is actually a pretty useful sort of theorem to have lying around sometimes. I'm not going to fully write out the last one, or sorry, this is the second to last one. But this is sort of your algebra of sequence limits theorem. So you've seen theorems that look like this many, many times now, right? So it says, for example, if AN and BN are two different sequences and they both converge, and AN converges to L and BN converges to M, then the sequence defined by AN plus BN converges and it converges to L plus M. And then it works for sums and differences and products and quotients under certain conditions. And then here, powers and lots of other things. Okay, I'm actually going to give you one of these in the homework to prove, but the proofs are very similar to all of the other ones we've seen. And then the last one, we've talked about this before in chapter 1. You get the sandwich theorem, or sometimes called the squeeze theorem. And so these are all sort of the basic properties that you really get more or less for free from definitions of what it means for a sequence to converge. All right. So again, I'm not saying the proofs are trivial. Okay, you should again carefully read the book. It has the proofs of all of these, but you know they follow more or less immediately from the definition. So by reading these and making sure you understand them should help make sure you really understand the definitions as well. So I encourage you to work through all of these. All right. Now, one of the things that's still sort of frustrating if you're sort of thinking about where we are right now with sequences, is that a lot of this sort of requires, or for example, if I want to know whether or not a sequence converges, based on what we said so far, still the only thing I have to go on is the definition, okay? And the definition of sequence convergence requires that I have some idea of what the limit ought to be, right? Because I need that L in my definition of convergence. But that can be hard sometimes for a number of reasons, either because you've sort of constructed a sequence, but it's not super specifically defined, like you may not have a particular function that defines the sequence, or at least you don't have some explicit form written down for the function. So that's sort of hard to work with and figure out what L is. So what we'd like some theorems that tell us a sequence converges even if we don't know what the limit is. And so the first theorem, and this is theorem, this is 2.53. This says if AN is a bounded increasing sequence, then AN converges. Now, again, sort of pluses and minuses. This is a theorem that gives me some conditions that if those conditions are met, I immediately know that the sequence converges. On the downside, I have no idea what it converges to. Okay, so that's going to be a little tricky, and in particular, this one's going to be tricky to start with because the only way I can prove this theorem, my conclusion needs to be that this converges, and the only thing I have is the definition. So actually, I have to somehow define what I think this thing is going to converge to. Okay, so there's a little bit of work to be done here. This is often also, this is an example of what's often referred to as the monotone convergence theorem. I should caution you that there are sort of many flavors of things that are called the monotone convergence theorem. They all in spirit are the same. They say if you have a bounded monotone sequence, then it must converge. But there are versions of this for integrals and lots of different things. So if you just start sort of willy-nilly Googling monotone convergence theorem, you might get a lot of different things. But this is one version of this. All right, so let's look at how we might go about proving this. And again, as I said, the only thing we have to work with right now is actually the definition of convergence. So I need to propose a limiting value here. Proof. So I'm going to let L be equal to the supremum over all natural numbers n of a sub n. Okay, now, as soon as I write this, there should be some questions that pop into your head. Okay, the first is, how do I even know that such a supremum exists? Okay, well, my set AN is bounded. Okay, since my set is, this is a set then of real numbers, or sequence of real numbers, it's bounded, so it's bounded above. So it has a supremum. Okay, so we're good. Whatever this thing is exists, it's some real number, and I'm just going to call it L. Okay, so this is, already you can see where I need the boundedness piece here. Okay. So let this be L, okay? And then I want to show then that this is actually the limit of my sequence, that the ANs actually converge to L. Okay, so what do I need to do? So I'm also going to need an epsilon. Okay, so take some epsilon greater than 0. Now, by the fact that L is a supremum, so by definition of the supremum, there exists a capital N, there exists a capital N such that A sub capital N is greater than L minus epsilon. Okay, now let's talk about why this is true. So L is the supremum, and the supremum is the least upper bound. Okay, so what does that mean? That means that this is a number such that if I decrease it any at all, it is no longer an upper bound. So when I look at L minus epsilon here, L minus epsilon is less than the least upper bound. So that means that L minus epsilon is no longer an upper bound for the set, for the sequence A sub n, which means that there must be some element of my sequence which is greater than L minus epsilon. Otherwise, if there was no element of my sequence which was greater than L minus epsilon, then L minus epsilon would be an upper bound, which is smaller than L, which can't happen by definition. L is the least upper bound, right? So by the definition of the supremum, there exists some capital N such that A sub capital N, that one specific element of my sequence, is greater than L minus epsilon. But what do I know? I actually know that this sequence is increasing also. So since this sequence is increasing, if A sub capital N is bigger than L minus epsilon, then A sub capital N plus 1 would be bigger than A sub capital N, so it would also be bigger than L minus epsilon. And I can keep playing this game, right? So since A sub n is increasing, then A sub n is greater than L minus epsilon for every little n greater than capital N as well, right? Because all of the A sub n's are getting larger. So if this one's bigger than L minus epsilon, then so are all of the other ones. Okay. All right. So then what do we have? Well, we also know that this thing, right? Again, L is the least upper bound, so it is an upper bound. So every A sub n is also less than or equal to L. What is this telling me now? This tells me that every element of my sequence where n is greater than capital N is trapped between L and L minus epsilon. So it's trapped in that epsilon band that I want. So if we sort of want to maybe formally write this out a little more algebraically, so I'm going to sort of flip some of these inequalities around and say, so I have L minus epsilon is less than A sub n is less than or equal to L, which is less than L plus epsilon. And now this piece only holds, and hence this whole line only holds for all n greater than that capital N. And so now if I look at this, so if I sort of ignore this L piece here, so I have L minus epsilon is less than A sub n is less than L plus epsilon. I can subtract an L everywhere. And now what does this really say? This really says the absolute value of A n minus L is less than epsilon for all n greater than capital N. Okay. And so an converges to L, which is exactly what I wanted, right? I wanted to show that this sequence an, which was bounded and increasing, converges. Okay. Now, yeah, I've shown it converges to L, but L is sort of defined as the supremum of this thing, which in practice would be just as difficult to find, right, as finding the limit from a function. So it's sort of, this is helpful for the theory for actually proving this. It's not super helpful when you're actually trying to compute the value of a limit. But this is nice now because, okay, I have some way of knowing whether or not a sequence converges without actually having to find what it converges to. All right. So let's now look at another theorem, sort of in this same spirit. This is theorem 254, which is also known as the Bolzano-Weierstrass theorem. So let me write the theorem and then I'll talk about it. So every bounded infinite set of real numbers has an accumulation point. Okay. Now, if we sort of combine this, you'll often sort of see this written in another way, which is every bounded sequence has a convergent subsequence. Okay. And so I want to first just point out that these really are sort of saying the same thing. Or actually, what I really should say is actually the first one implies this. So if I take a bounded infinite set of real numbers, okay, this theorem says it has an accumulation point. Well, if it has an accumulation point, then I should be able to take elements of this set and construct a sequence which converges to that accumulation point. Okay, so these are sort of really the same in spirit, and sometimes it's easier to use this piece. But sort of fundamentally, what this is trying to get at is the question of like whether a set will have an accumulation point at all. Okay. So let's look at the proof of this theorem and erase that. Start the proof. So let E, so E is just going to be my bounded infinite. I'm just going to say the bounded infinite set. It's a set of real numbers here. And that is important, that it's a set of real numbers, but I'm not going to write all that out. All right, so let E be my bounded infinite set of real numbers. Since E is bounded, there exist real numbers. I'm going to call them A1 and B1, such that E is contained in the interval A1, B1, right? It's a bounded set. So there's some upper bound, let it be B1. There's some lower bound, let it be A1. and such that my set E must be entirely contained within A1, B1. And okay, it's possible that E is exactly that set, A1, B1, but let's just, I just sort of need these things to start with. So now what I'm going to do is, I'm going to define another point C1. And C1, I'm just going to take to be the midpoint of A1 and B1. So let me sort of draw a picture, sort of what's going on here. All right, so I'm going to draw in red. So my set E is some collection of real numbers, so it could contain all sorts of it. So maybe it contains the small open interval, and then, I don't know, 3 more points here, and then, I don't know, maybe it has sort of a dense set of points here. I mean, right, it could have all sorts of things, okay? And so I've chosen my points A1 and B1, and maybe just to be a little ridiculous, right, I'll say I chose A1 here, and maybe I chose B1 sort of over here. Okay. And now I'm going to define C1 to be the midpoint of these two. And sorry, actually, right, I think I did not define that correctly. Oh, wait, no, sorry, I did. Hold on. There might be a typo here. Give me 1 second. All right, yeah, sorry. There's actually a typo in the book. So I wrote down originally what's in the book and then realized, well, that's not quite right. So right, this should be, to be the midpoint, this should be A1 plus B1 over 2. And the average value of the two would be the midpoint. All right, so this point C1 maybe, I don't know, ends up being sort of here. All right, now my next step in the proof is going to be, I'm going to look at these two intervals. I'm going to look at the interval A1 to C1 and the interval C1 to B1. And at least one of those intervals must contain an infinite number of points. Now, why is that? Well, my set E, right, is an infinite set. So there are an infinite number of red points here. Well, if I split these up, then they can't both contain a finite number of points, right? If both of these intervals contained a finite number of points, then my whole set E would be finite, which isn't true. So at least one of them, possibly both, must contain an infinite number of points. I'm going to choose one of them that has an infinite number of points. So like in this example, it sort of looks like maybe this interval is the only one that contains an infinite number of points. Maybe this has a finite number of points. Okay, so if there's only one that has an infinite number of points, I'll choose that one. If they both happen to have an infinite number of points, then just choose one of them. It doesn't matter which one. Okay, so the thing I want to do now is, so since, let me write out what I just said. So since E is infinite, either A1, C1, or C1, B1 contains an infinite number of points. And again, this is not like the exclusive or, right? It's possible that both of them contain an infinite number of points, but at least one of them contains an infinite number of points. Okay, and so I'm going to set A2, B2 to be the, say this, to be the interval which contains infinitely many points. All right, So a couple of observations once we do this. So the first, right, is that this is now a subinterval. Right, A2, B2 is a subinterval of A1, B1. And in fact, it's a strict subset, right? These are a strict subset here. Okay, so even though I've written, even though I've put equal to on both of these, you're only going to have equality on one of them. Okay, so that's great. And the second thing I'll point out is that B2 minus A2 right, the length of A2, B2, well, A2, B2 is either this interval or this interval, and because I set C1 to be the midpoint, the width of this new interval is exactly 1/2 the width of the previous interval. Okay? So the width of A2, B2 is 1/2 the width of A1, B1. Okay? So now I'm going to repeat this process. So repeat the process. And when I say repeat this process, what I mean is, okay, so now I've got A2, B2. Let's say it's here. Then I'll choose C2, that'll be the midpoint of that. Then one of these subintervals will have to contain an infinite number of points. Okay. I'll choose that to be my new subinterval. Okay, then I repeat and I keep going over and over and over and over again. Right? So repeat the process so that let me come back over here. We have sequences AK, let's see this, yeah, that's fine, AK and BK, so that I have 1 is less than or equal to A2, is less than or equal to A3, is less than or equal to B3, B2, B1, right? So I sort of have this sort of ordering on these sequences. And if I look at BK minus AK, well, I know that that would be 1/2 of BK minus 1 minus AK minus 1. But I can actually then iterate that process, right? So this thing would be 1/2 times BK minus 2 minus AK minus 2. Okay, and I can repeat this process, so I actually end up with 1 over 2K times B 1 minus A1. Okay, oh, and sorry, K minus 1. Right? So when I was at BK, I went down 1, that pulled out a 1/2. I can go all the way down. By the time I get down to 1, I will have gone down by K minus 1 terms. So I'll get a 1/2 to the K minus 1. All right. All right. So let me think about these sequences AK and BK. Well, let's look at AK first. AK is what kind of sequence? Well, it's a sequence which is always increasing, right? It's monotone, or actually it's non-decreasing, but it's monotone, and it's bounded. In fact, it's bounded above, say, by B1. Similarly, if I look at the sequence BK, this is a decreasing sequence, still monotone, which is bounded below by A1. It also converges, okay? So the sequences AK and BK are both monotone and bounded, and hence converge. And they converge by that monotone convergence theorem that we just proved. All right. So suppose AN converges to A. So I'm just giving names to their limits. And BN, or sorry, AK converges to A, and BK converges to B. Okay. Well, since BK minus AK is equal to 1 over 2 to the K minus 1 times B1 minus A1, then if I take a limit of both sides as K goes to infinity, then I get the limit as K goes to infinity of BK minus AK, which, by the way, that should just be equal to B minus A, right? But I also have that this limit, so let me rewrite this a little bit. So B minus A, since these converge, this is the limit as K goes to infinity of BK minus AK. So this is the same as the limit as K goes to infinity of 1 over 2 to the K minus 1 times B1 minus A1. But if I look here, as K goes to infinity, this term is going to go to 0, and that's fixed. So that limit is 0. So I have B minus A is equal to 0. So A is equal to B. Okay. And so what does this tell me? So that tells me that, right, so the limits are equal here. Again, what was I trying to prove? I was trying to prove that this thing, that this sequence has an accumulation point. Okay. And so what I want to show then is that this common thing that both of these sequences converge to is in fact the accumulation point I want. Okay. And that's just sort of the last sort of piece I've got to reason through. So then, since both of these sequences converge, well, what does that tell me? Then, given any neighborhood of, so I'm going to take this common point, so I'm just going to call this thing A from now on because they both converge to A. So given any neighborhood of A, I can choose well, for example, I could just take A sub K here, or sorry, I could choose, sorry, a natural number N, so that A sub K minus A in absolute values is within, so sorry, I need to give any neighborhood of A with radius capital R, right? I can always choose a natural number large enough so that a sub k minus a will be less than r for all k greater than n, because now I know that these a sub k's converge to a. Okay. And so that tells me then that there's some element, so a sub k, or sorry, let's just take a sub, say, capital N plus 1. So if I take k to be equal to capital N plus 1, that satisfies this, so this must be the same. So then a sub n plus 1 is something in E. Okay. And a sub n plus 1 is in the neighborhood of radius r around A. But it's also not A. Okay. And so A is an accumulation point. Accumulation. Why? Because I've demonstrated something that is in the neighborhood of radius r around A that is not itself A. And this works for any arbitrary radius r. All right. So now I have a description now. If I have a given set, and I know it's a bounded set and contains an infinite number of things, I know it has an accumulation point. And again, another way of sort of utilizing that is to say that I know that if I have a bounded sequence, that sequence will have a convergent subsequence. Even if the sequence itself may not converge, but if it's bounded, it will have a convergent subsequence. All right. So the last theorem I want to look at that's sort of similar in spirit to this. This is again sort of something that allows you to say something converges without explicitly knowing what it converges to. Is I want to introduce the idea of what it means for a sequence to be Cauchy. So first let me start with a definition. A sequence AN is a Cauchy sequence if and only if for any epsilon greater than 0, there exists a natural number n, or capital N, such that an minus am is less than epsilon whenever n and m are greater than capital N. So again, this is, it looks similar, very similar to the definition of convergence, but it's a little bit different, right? Really, the definition of convergence says that if you go out far enough, the elements of your sequence must be getting close to some limit value. What this is saying is not that the elements of the sequence are getting close to some particular value, but rather that as you go out far enough, you can make elements of the sequence arbitrarily close to one another. Okay? You might think very reasonably, well, that sounds sort of like the same thing. And that's because the next result we're going to show is that a sequence is Cauchy if and only if, a sequence of real numbers, sorry, is convergent if and only if it's Cauchy. Okay? In order to do that, we're going to need a lemma. Actually, I'm going to call it a separate theorem, because this is a theorem I'm going to ask you to prove in the homework, but I don't want to take time to do it right now. So every Cauchy sequence bounded. So I'm going to need that for my next proof. Keep in mind that we showed, or one of the results that's proved earlier in the book is that every convergent sequence is bounded. I would go take a look at that proof and see if you can adapt it rather for the setting we're in here, where we don't have convergent sequence necessarily, but we just have a Cauchy sequence. So here's the theorem I want. A sequence of real numbers is convergent if and only if it converges. And maybe the channel that I'm looking at the book, they write in the reverse order, but it's if and only if, so it doesn't matter. All right, so let me actually I'm just going to do the reverse direction first. Okay, so if it converges, then I want to show that it has to be Cauchy. Okay. The book hand waves this a little bit. It's a simple application of the triangle inequality, which is not false, but let's actually take some care to write it out. So assume that the sequence A sub n converges and to some limit L. Okay. So my goal is now to show then that it is Cauchy. Oh wait, I just realized I guess I couldn't decide. So what have I written? A sequence of real numbers is convergent if and only if it converges. Well, that is also true, but that's vacuously true. So okay, let's write it in the same way. The sequence is Cauchy if and only if it converges. And then, okay, now I'm proving that direction. Assume it converges, show it's Cauchy. Okay, so assume AN converges to some limit L, then I want to show it's Cauchy. So since it converges to some limit L, let me let epsilon greater than 0 be given. And I'm going to choose a natural number n such that AN minus L is less than, and I'm not going to use epsilon here, I'm going to use epsilon over 2 here. So AN minus L is less than epsilon over 2 for every little n greater than capital N. Why can I do this? I can do this because my sequence is convergent, right? That's what it means for a sequence to be convergent. I can always choose a capital N such that whenever little n is greater than capital N, AN minus L in absolute values can be made arbitrarily small. All right. Now take little n and little m greater than your capital N. And then I want to look at AN minus AM. All right. One of the greatest tricks in analysis, add and subtract the same thing in between. So the idea here is I don't know anything about these two in relation to one another, but I do know things about these things in relation to the value L. So I'm going to rewrite this as AN minus L plus, or sorry, minus AM minus L. Now, if you look at this, these are just equal. I've really just added and subtracted L in here. So I haven't changed the value. Okay. But now I'm going to apply the triangle inequality to this. I'm going to run out of room maybe, but I'll try and squeeze it in here. So this is AN minus L in absolute values plus AM minus L in absolute values, right? Okay. So I've just broken this up using the triangle inequality. But now what do I know about this? I know that this is less than epsilon over 2. And I also know that this is less than epsilon over 2 because both n and m I've chosen to be greater than this capital N. And whenever these things are greater than capital N, then this inequality holds. So each of these is less than epsilon over 2, so the whole thing is less than epsilon. And so I have AN minus AM is less than epsilon when n and m are greater than this capital N, which is exactly what I want. So that's the first half of this. And so I've shown that if I start with a convergent sequence, it must be Cauchy. Now I've got to try the other way around. Erase the definition of Cauchy. All right. So now here's the forward direction. So let AN be a Cauchy sequence. And this is where we're going to need the result that you're going to prove in the homework. And then AN is also bounded. Okay. So now I'm going to define a set. So set E to be equal to AN. Now you might be wondering, what is E and why is it different than AN? Really what I'm thinking of here is E is not a sequence, it's just the set of values that the sequence takes on. It could, for example, be a finite set. So if you take the sequence -1 to the n, then the only output values you're going to get are going to be 1 and -1. And so your set E would be a set which contains two things, 1 and -1. So E is just sort of the set of all output values. I'm not really worried about the ordering anymore. Okay. But since AN is bounded, then E is also bounded. It's a bounded set. So now let me break this into a couple of cases. So if E is finite, okay, so let's take the case that E is finite first. So if E is finite, what does that mean? That means your set only attains some finite number of output values. Okay. But I also know that my sequence, in this case, sorry, is Cauchy, which means that the terms of the sequence are getting close together. Well, if it only has finitely many output values, and as you go far enough together, they're getting closer and closer, then it must be converging. There's no way it couldn't converge, right? Because think about what would have to happen. So in order for a Cauchy sequence which has a finite number of output values not to converge, you'd have to have these things be getting closer and closer together, but never converge to anything, right? So every time you take a step out, you need a new output value of your thing so that it could get closer, but not end up being one of these things. So if E is a finite set, then AN is eventually constant. And this is the thing I briefly explained, but I'm going to ask you in the homework to prove this more precisely. So AN is eventually constant and hence converges. So, again, let's take some justification, and I'll have you work on this in the homework. But if there are only a finite number of outputs, then your function, or your sequence, since it's Cauchy, eventually has to just be one of them. And therefore, well, if it's eventually the constant sequence, then it converges. Okay. The slightly harder case, so if E is infinite, well, now let's see, if E is infinite, then I have my set E is infinite and E is also bounded. So we just looked at the Bolzano-Weierstrass theorem, which tells us something about bounded infinite sets. So if E is infinite, then by, and I'm going to abbreviate that BW, so by the Bolzano-Weierstrass theorem, E has an accumulation point. and we'll give it a name, capital A. All right. Now what I want to do is I want to show that this capital A is the limit of my Cauchy sequence AN. Okay. Let me move back over here to finish this off. All right. So what does it mean for A to be an accumulation point? That means that if I take any neighborhood of A, that there are points in E, which are not the point A, in the sequence. So consider the interval so sorry. I need epsilon first. Let epsilon greater than 0, and consider the interval A minus epsilon over 2 to A plus epsilon over 2. Okay. And I'm going to make a claim here, which contains an infinite number of points of E. And what the real claim here is that it must contain an infinite number of points. So why does this interval contain an infinite number of points of E? Well, if we were just looking at this interval, the fact that A is an accumulation point tells me that this interval, because this is a neighborhood around A, it must contain at least one point of E. But right, I could create a whole bunch of other intervals that are contained inside here, right? So say you find some point that's in this interval, then I can take a smaller neighborhood that excludes the first points you found, but is still a neighborhood around A, and I could find a point inside there, and I could repeat that process over and over and over again. So this interval must contain an infinite number of points of E. All right. And hence, an infinite number of points in the sequence. Right? So since my sequence AN is Cauchy, there exists one natural number n, capital N, such that when N and M are greater than capital N, AN minus AM can be made as small as I want. I'm going to make it less than here, again, epsilon over 2. Okay, and now what I want to do is I'm going to choose a point, XM, which is in this interval, A minus epsilon over 2 to A plus epsilon over 2, with little m being greater than capital N. And now, why does, and you might ask, sort of, why does such a point, exist at all? Okay. So if I go out far enough in my sequence, right, I'm going to have to sort of go out sufficiently far to end up within this epsilon range anyway, right? And so as I go sufficiently far out, those points will be close, okay? And so it'll be in this interval. Sorry, I think I've got another typo here. Let me check real quick. Yeah, sorry. This is not XM, right? This is AM. And so AM is a point in my sequence that's lies within this set, but is sort of far enough out in my sequence to be within A minus epsilon over 2 plus A plus epsilon over 2. All right. And then, okay, finishing this up. Now I want to look at AM minus AN. So then when little n is greater than capital N, I want to look at AN minus this accumulation point A, because again, that's the thing I'm thinking is my limit. Okay. Well, this will be equal to, again, let me play the same trick as before, but now I'm going to add and subtract this point AM. And I'll apply the triangle inequality. And now if I look here, my sequence is Cauchy, so this can always be made less than epsilon over 2. And in fact, we've already said, right, this is less than epsilon over 2 when n and m are greater than n. But remember, I chose this point AM to lie in this set. And so this distance must also be less than epsilon over 2. And so what do I have here? I have that AN minus A is less than epsilon. And so AN converges to A. The book points out, and it's nice to look at this example, that this only works sort of if you're looking at the real numbers. So if you try to look at the rational numbers, you can construct sequences of rational numbers which are Cauchy, but they don't converge to another rational number. So for example, if you can look at sort of approximations of pi, for example. I think that's what he does, as a matter of fact. Yeah, looks at approximations of pi, and you show that that forms a Cauchy sequence, but it doesn't convert. It converges to pi, right, which is not a rational number. All right. So the last sort of piece of this, so this is sort of everything I want to say about sequences. The last sort of thing I want to mention is that we're going to start next time talking about series. And so I want to just quickly define a series and say that, okay, you know, we actually get some sort of things for free if we sort of define things in the right way. So for any sequence, starting with a sequence, any sequence AK, we can form the sequence of partial sums Sn is equal to the sum K equals P up to N of A sub K for a fixed integer P to generate the series to generate the sequence Sn. Okay. So you've probably seen this before. We're working our way up to an infinite series. we want an infinite series, and we're going to look at this sequence of partial sums. So the partial sums often, right, our p-value is 0 or 1, right, depending on where sort of we're starting from. But this will generally just say we can start at some integer value, and then the sequence of partial sums is just working our way up from there. And we also say then the infinite series, which I'll call S, which will be the sum from k equals p to infinity of a sub k. This converges if and only if this sequence of partial sums, Sn, converges. Right. So the book then walks through some examples, and I'll talk about a couple of those in a minute. But I just want to point out that if you then look at theorem 2.58, which is the Cauchy criteria for series, it's essentially just taking what we know about Cauchy sequences and applying it to series, where we're thinking about series through this sequence of partial sums. Okay, so there's sort of some benefit where we've done all this work for sequences, and we can sort of immediately carry some of that over to series. But it ends up being that a lot of times this is sort of more complicated to work with than we really want, or they're just much harder to apply because this sequence of partial sums is a very complicated sequence to work with. So what we're going to want to do next time is sort of develop some more tools for dealing with these things. So just to sort of get your brain moving in that direction, and this will be the last thing we'll do for today. I always sort of love looking at the following. So let me look at the infinite series sum n equals 0 to infinity of -1 to the n. You know, this is a really fun one if you're teaching Calc 2 sometime, where you're usually talking about sequences and series to sort of mess with your students with. And by mess with, I mean get them to think deeply about this. So when I start writing this out, which is often the tempting thing to do, so I get 1 plus -1 plus 1 plus -1 plus 1 plus -1, dot, dot, dot. And there's a temptation, especially among Calculus 2 students. They look at this and they say, oh, okay, I'll group these together, and I'll group these together, and I'll group these together. And in their minds, they're saying, well, addition is associative. This is okay. And it is true that for any finite number of these, this would be okay to do. But when you write out the properties of addition, right, it's sort of really focused on finite sums. Then you have an infinite sum. So they're tempted to do this and go, oh, well, each of these is 0. So this sums up to 0. Perfect, no problem. Okay, and then you play devil's advocate with them, and you say, okay, so you did it that way, but let me do it this way. Well, I'm going to just take your parentheses. I'm going to sort of shift them, right? And so I'll put my parentheses here and here and here and so on. And so I'll get 1 plus 0, 0, 0, 0. So this sums to 1. Okay, and that usually sufficiently well messes with them. And then if you really want to mess with them, and in the book they mention this briefly, another way to look at this is to say, well, okay, I don't know exactly what this thing is, but let me call it S. Right now, I'm feeling unsure now. So let me just write this, and instead of plus negative, I'm just going to start writing minus. So on and so on. So I don't know what the sum is, but let me call it S. And now let me look at what would 1 minus S be equal to? Well, that would be 1 minus 1 minus 1 plus 1 minus 1. So I'm going to get 1 minus 1. So these will definitely cancel. And then I'll end up with 1 minus 1 plus 1 minus 1. So if you see these cancel and then you distribute the negatives, so actually see that I just get S again. And so what I have here is I have that 1 minus s is equal to s, and that's nice because this is an algebraic expression which I can solve, and I get that s is equal to 1/2. Okay. Now, of course, all of these are wrong. And the truth of the matter is that this is a really good way to get back to the definition. Let's look at the sequence of partial sums here. Okay. So the first partial sum, right, is just the sum of the first thing. And so S1 is 1. S2, capital S2, is the sum of the first two things, that's 0. S3 is the sum of the first three things, that's 1. And you're starting to see that the sequence is 1, 0, 1, 0, 1, 0, 1, 0, which doesn't converge. And since this sequence of partial sums does not converge, this series does not converge, and therefore all of the stuff we were trying to do to it really didn't make any sense, because we were messing with some object that really didn't represent a real number at all to begin with. Okay. So next time what we'll do is we'll start building up. Many of these are tools, again, you've seen before, so things like the root test, the ratio test, things like that. But again, we'll start building them from a more fundamental level, and not, we won't be so focused on just applying them, although we'll talk about that a little bit too, but more about sort of why are these theorems true. All right.